Yes, thank you so much. Thank you all for sticking around. My name is Pablo Damasceno. Thanks for the invitation. Thanks for the previous speakers for the talks. I learned a lot today. I am a senior data scientist at Janssen Pharmaceuticals, which is part of Johnson & Johnson. You might know us by the vaccine for COVID-19. And just I have one quick slide about me. I have, so you know who I am. My name is Pablo Damasceno. As I mentioned, I have a PhD from the University of Michigan in Applied Physics. I've worked for the past 6 years at UCSF, developing and testing and deploying machine learning algorithms in the clinic, working very closely with doctors to make sure ML and AI algorithms were being used at UCSF. And in the past 2 months, I have joined Janssen in the computer vision division that we have in data science. In fact, tomorrow I'm going to go across the country to move to Boston, and this is the reason, actually, I'm dressed today as a normal driver as opposed to how I would usually come here with a suit and everything. My movers yesterday packed everything, including the clothes I was gonna be using today. So tomorrow I'm going to be driving to Boston to really start at Janssen. So here are my disclosures. I worked in a number of projects in collaboration with these companies. And if you're interested in computer vision at Janssen, please drop me a message. We are hiring. So I'll be talking about 2 projects today. Very quickly going to mention, and just I should say that both of those projects were done at UCSF while I was there. Very quickly, I'm going to talk about a project we've done with COVID-19, and then I'm going to move on to talk about some tumor segmentation in the area of neuroscience. So about COVID, if you remember 2 years ago, one of the major issues that hospitals had were the lack of ventilators. And one question that everyone had in their minds was, can we predict whether a patient that comes today, if they're gonna need a ventilator or not? Because if you can predict, we can try to manage the resources. And even better, if you can predict that this patient is expected to die in the next 24 to 48 hours, you could try to, again, manage resources and try to make this patient, make sure they have the care they need. The problem was that if you wanted to make a deep learning algorithm to work on this field, in the very first few months, nobody actually had enough data. It was basically each hospital had a few hundred cases. Even if you had thousands of cases, perhaps only a few hundreds of those had a chest X-ray that you could then use to train your model. This plot here shows the data in black is the data for the entire UC system, so UCLA, UCSF, UCSD. And what you see is that each individual hospital had only in the order of a few thousands of patients. That was a time that NVIDIA actually got in contact with us and said, hey, we are coming together and creating this platform for federated learning. And I'll show we had already great talks today talking about this subject. And the idea here was, we are gonna ship you a Docker container, you put in a machine, and then you train this model in your data. And the weights of this model are gonna be sent, only the weights, the data stays where each of the hospitals have the data. The weights are going to be sent to a AWS server. This model is then going to average all those weights, perhaps a weighted average based on the data for each of the sites. And then we're going to send the weights back to you. And then you have a model that was basically trained in a bunch of different institutions. And that was great. We accepted this invitation, and we were part of a network of 20 institutions that used a model which is called the deep and cross. So what this model does is that we had the chest X-ray for the patients, and we also had a bunch of electronic health records data. And you wanted to combine these with the images, and this is what this network does. It takes the features of a ResNet, there is some cross terms in here, and what we were predicting in the end is, what's the probability that this person needs a ventilator? Are they gonna be in room temperature? They're gonna need a ventilator, a very high flow ventilator. And what's the probability that this person is going to die in the next 24 hours or 48 hours? So as I mentioned, we were one of 20 institutions all over the world. You can see here different places that were part of this federated learning model. What is really interesting here is that some universities contributed with a lot of data in the order of thousands of patient data, images, and EHR, electronic health records. And most of the institutions, we have this heavy tail. Most institutions have very little data to contribute. But that doesn't necessarily mean that this was not useful, because if you look, for instance, at this distribution of age, some of those hospitals were children's hospitals, so all the data was for children. If you had trained a model only in adults, it would not have worked for children, and vice versa. And what we have seen then was that by training the model in this way, I'm skipping over a whole lot of details, but this is published work that I'll show in the end. You can just go to the publication for details. But what I'm showing here is that in green is the federated learning model. So this model that was just the weights were being transferred between institutions. And when you take this model and you're applying the test set for each of the institutions, so you take the federated learning model, you go to test one and say, to site one, say, hey, give me your test data, apply this model. It consistently works better than the model trained on that institution. So the model has higher accuracy. The model is also more robust. Then we took 3 other hospitals that were not part of the federated learning, applied the model. It works better there too. And another thing that we did was, well, you can say it's not completely private if you're sending those weights around. Can't I get information from the patients about if I can intercept those weights? Another thing we did was to see how much can I just send a few weights, and it turns out that sending 30% of the weights between institutions in the central site gave basically 90% of the performance. So if you're still concerned about your data, or in this case, the weights being moved around, you can shuffle those weights, you can send just 30% of those weights and still keep your model with a high accuracy. So this all worked. Basically, NVIDIA contacted us in March, and it took us, this is 8 months from beginning to end. And in academia world where I was from before, this is unheard of. Basically, in 8 months, getting 20 institutions all over the world to come together to solve a problem and get a paper written, this was crazy for me. And actually, the hardest part was it took 8 months for us to do the job. It took then 1 year for the paper to get over reviews and published. So that was the longest part and hardest part of the work. So this is what we've done for COVID. I'm going to switch gears now and talk about another problem that uses computer vision, which is that of tumor segmentation. In this case, particular in brain tumor. So a lot of hospitals use CSF, but most hospitals that have a neuroscience division, they will monitor patients with brain tumor. And it was, again, crazy for me not being a clinician to learn this, but a lot of people that have brain tumors, they can have a brain tumor the size of a golf ball in their brain and perform completely normal, day to day. Their daily lives are completely normal, because if this tumor is growing very slowly, your brain can adapt. And all these neural nets, no pun intended, but the neural networks in your brain literally are going around this tumor, and if it's growing slowly, they can just plastically move. And what the doctors decide to do is not to remove this tumor unless it starts to grow exponentially, which means, okay, now it's in a stage that is going to start to break a lot of those connections, and we should do a surgery there to remove. Why wouldn't they just remove from the beginning? Because there's always a probability that something is going to get cut that shouldn't be during the surgery. So they monitor, they bring the patient every 3 months, they scan them, and they ask, is this tumor growing exponentially, or it's basically about the same size? You would imagine that what they do to measure this is to do some kind of analytical calculation of the volume, but they see so many patients. I've shadowed some of them, and I just saw that over an hour, they're looking over 20 patients. And they have to go over the history, what's they scan in the last 3 months, 6 months, last year, look at the images, try to find out, did it grow, did it not grow? I don't think it did not grow. And the process is very subtle, because this is growing slowly sometimes. It's very time-consuming, because they have to look at all those images. It's very reader-dependent. You get 3 radiologists in a room, you get 5 different answers. And it's very qualitative, because they are actually not going to say, this is growing exponentially, because they're not measuring it. So when you look at the radiology report that is then passed to the neurosurgeon, they're going to have very qualitative sentences like, this is suggestive of progression, or there is some slow growth, or may represent progression, because they're being vague on purpose. And just as a side note, just for me to find this data set of people who had progressed versus non-progressed, I had to develop an NLP just to read those reports and understand which ones progressed and did not, because they're being so vague that just a regular expression here did not work on the radiology reports. So what they wanted was a model that was accurate, that can tell me if there is progression or not, that's interpretable, because if you just say, here's a black box that is saying this patient's tumor is growing, they are not going to use it. And it should be fast, at least in the range of hours. It's not the edge computing here. We're not talking about I need this answer in seconds. But it should be, it takes them about 20 minutes per patient. So if you could give them the solution within 20 minutes, then you're not really, you're helping their workflow. If it's in an hour, they're not going to use. So what we did was, here are some inputs, use straight off-the-shelf UNet. And the point here was, can we just take things that are already known to work, like a UNet, and segment this problem? Where is the bottleneck if I want to apply this to the clinic? We take those images, we throw in the UNet, we get segmentations, and then we give them a volumetric plot of what's happening to the tumor volume over time. So very quickly, in terms of what I use to do this, it's a bunch of MRI images that they're all put in the same resolution so that the same neural nets can be used. We had around 600 images, and I got some radiologists to help me segment the tumor in all those 600 images. They did not want to do it, so I had to come up with a different approach. And then the approach here was to do active learning. I said, okay, let's compromise. Can you segment 30 images? And they said, okay, I can do 20. So then they did 20. I trained a neural net that then segmented another 100. This 100 that is segmented was not very good, but at least for them to go and annotate this 100 and improve on the algorithm was a lot faster than segmenting from scratch. So then they did another 100. Now I have 120. I trained the model again. I gave them another 100. And we slowly converged to a number of 600 manually segmented images. As I said, I use a 3D UNet that is available. You just Google your favorite UNet. Did some data augmentation like anyone would do. And the deployment part was also in a collaboration with NVIDIA that had some, what's called NVIDIA Clara, has some orchestration for getting data from the scanner, kicking in a pipeline, and allowing the results to go into a database. And I'll show this in a second. And for results, I don't know how much, for segmentation, you're probably familiar with dice score, which is basically how much of my segmentation agrees with the manual segmentation. And we got around 87% agreement. And when I take a bunch of patients that progress or did not progress, I get a sensitivity and specificity about 0.7. So let me show you how this worked in practice. A radiologist in the office, and they find a patient that just came and had a scan. And this part here, which is brighter, this is the tumor, this whole brighter part here. So what they do is, okay, I want to see the volume for this patient. They send this image to a machine, which is in our cloud. I guess it's a private cloud within UCSF. And this kicks in a pipeline that is going to take this image, make sure that this image is a MRI for brain and all this, so that our model is not running some different data. It is really fast to kick in an inference model. So this is not real time, but the whole process takes about 5 minutes. So to getting this image, running the segmentation, sending the data back to a database that the doctor can access through the browser. And from the browser, they're able to open the image again, load the image, make sure it's the same patient. They see that the tumor is still there. They can then load, and this by now, this is all automated, but can load the segmentation. And this was when they gave us some feedback and say, I'm not going to use this. I'm like, why not? They're like, well, it's missing some parts. And if you don't allow me to go there, and even though before, they remember, they were doing by eye. So when they make some edits, they're actually editing things of the size of like 1 to 2 millimeters, but when they are doing by eye, they're making mistakes on the order of centimeters. So, okay, but we went there, we gave them the possibility of going there and editing those segmentations, and then they can give us some feedback on that. And then, of course, we can use this data to retrain the model, right? So here's what we presented them in the end. What we have is this patient comes today, they had a visit. We go find this patient, find all the other visits for the same patient in the past. We calculate the brain tumor segmentation. This data is then sent to the radiologist. They see a plot with the volume. And what happens is they have a threshold that's dictated by the Neuroradiology Society that if the tumor grows over 40%, that's when you should do something about it. And in this case, that's why on B here, I have the different visits. I have the volume in this column, and I have the change in here. And if the change goes over 40%, then it's marked as, hey, this is a progression. You should do something about it. On the right, we have the segmentation images. They are able to go there and change those segmentations if they want to. So this was accurate, was fast, interpretable, and it was editable. But not everything was flowers. Sometimes there were edge cases, and sometimes there were mistakes. One of which was sometimes the scanners are changing. So some patients, in this case, this patient here, it was a patient from Tahoe or Reno, and every 3 months they would go to their hospital, which is close by, and then in the other 3 months they would come to UCSF. They have to make this trip. So we're not making them come here every 3 months. But then at their own hospital, the scanner has a bad quality. And just visually, the model, or even a radiologist, when we give the radiologist the image, they are not able to get the same volume that is as large as if you have a scanner with high quality, just because the pixels are not there. You cannot say where the boundary is. So we started to work on ways of introducing in the ML model ways to not care about the scanner, but meanwhile, and this again has been repeated over and over and over in this throughout today, human in the loop. Can we actually put a human if a human came here and saw this, they can just say, this and these and these are bad scans. I don't want to care about those. Just select the ones that came from your CSF, and I see that the volume is actually not changing. So as a stopgap solution, what we introduced was this human in the loop that is able to look at the images before it goes to the radiologist and makes his decision. The radiologist still has the ability to go there and see what's going on here. But they are able to see, OK, I'm only going to choose the MRIs with good quality. And this is something that I learned over time. There is this quote that I actually cannot find where it started, where it came from. But the idea of, if you're going to fail, fail like an escalator. Do not fail like an elevator. An escalator, when it fails, you can still use because it's a ladder. You can go up. If your model is going to fail, make sure that it's not in a way that they cannot do anything about it. Make sure that it's in a way that they can still understand what's going on and use that in their normal workflow. So finally, so the workflow now becomes the human in the loop is you have the data, you have the radiologist having the ability to do a manual curation of the data and select scanners if they will. And then finally, this is presented in a way of a volume plot that the radiologist can use and send to the neurologist who is going to decide whether to do surgery or not. And a final thing is that, OK, I had all this segmentation. Can we go one step further? We have all this information about the tumor. Can I actually do something that perhaps the doctor could not do? Can I actually predict, this person came today, they had a scan. It turns out that there was no progression. The tumor did not grow considerably. Can I predict what's going to happen in the next scan? And if I can obviously tell doctor to make sure this patient do not miss their visit, that they come. Perhaps there is some intervention that should already be done because we already expect this patient to be progressing the next visit. This is a slightly tricky problem because those patients are coming, but it's not always equally spaced. Sometimes they're coming every 6 months. Sometimes they're coming every 3 months. Sometimes they miss visits. Sometimes they come in different hospitals. So the data looks more like this. This patient came here and then came here. This other patient had a lot of visits. So how do you deal with this to create a model that can make predictions about whether they're going to progress or not in the next visit? Simplest, dumbest thing you can do is to take the last visit, which is the one you're interested in making a prediction, and making a delta. How much change is there between the last visit and the average between all the other visits? So between today when they came and the past, just take the delta and say, can I use that as a feature? If you do that in images, it's going to be really bad because delta images is complicated. So one way you can do is that you can first calculate a bunch of features. Once you have segmentation, you can calculate what's the size of the segmentation, what's the shape, what's the area, volume, what's the intensity of the pixels, what's the standard deviation of the intensity of the pixels, all this. And this is called in the field as radiomics. You're basically calculating hundreds of features. If you have hundreds of features, now you can calculate delta. And now you can do standard machine learning things, like you can take those features, you can do a lasso to only get the features that are important, then throw in your favorite machine learning model from scikit-learn, your random forest, support vector classifier, whatever. And this actually turned out to work somewhat. We only had 100 patients in this study. We had about 800 images, but because each patient had about 8 images on average for each patient. So in terms of patients, we only had 100. When you do separation between train, validation, and test, you end up only with 10 patients in your validation test or in your holdout test. Out of 8 patients that were progressed, radiology marked as progressed, the model predicted that 7 of them would progress, and we got 1 wrong. Out of 7 patients that did not progress, the model got 3 wrong. And then it took me about 3 months to get to this plot, and by that time, they already had another visit because they already came to the hospital, they had a new image. So I just asked the radiologist, hey, what happened to these 3? Did they actually progress? And then it turns out that they did. So the model got those 3 wrong because they did not progress in 3 months, but then they progressed in 6 months. And it turns out that the 4 that the model progressed to be stable, after 3 and after 6 months were still stable. So in a sense, the model kind of got those right. It just did not get exactly in the 3 months margin that I was looking for. So this is what I have, just 2 examples of clinical use of ML and AI. My message here today is that sometimes the clinical challenges that we have with respect to machine learning, sometimes they are new problems that require new solutions, like the federated learning problem. You need data, you don't have enough data, but maybe a combination of hospitals have enough data. So then you need a new solution like federated learning, where you're bringing you're bringing model to the data, and then you're sharing weights. And that worked really well for this particular problem. Other times, the problem is more about orchestrating existing solutions, as in the case of the segmentation here. The segmentation algorithm was already there. I did not create that. Algorithms for transferring data from the scanner to the cloud are already there. But then there are all those steps. It's like, where is the computer? What software is running on it? And how do you integrate all of these? So those are very mundane problems. But I feel like a lot of startups and a lot of ideas, they get to this 90% where they have a proof of concept that's working, but then it's never adopted because they're not taking the steps of actually implementing that in the clinic because that's actually hard. For now, I think human in the loop is going to be around for a long time, and I hope so, because I also don't want to go to my doctor and my doctor to say my ML says that you have cancer, and then you ask them, what's going on. They're like, I don't know, the ML told me so. So keeping the human in the loop and using interpretable models, I hope is still around for a while. And sometimes, let's also as a community think about not just automating the boring work, right? And I started with the problem of, can we automate the hard work of segmenting the volume of the tumor? It's expensive, it's tricky, and it's hard. But can we take one step further and say, can we make a prediction of what's going to happen in the next visit, which is something the doctor is not doing. They're not thinking, oh, maybe in 3 months your tumor is going to grow. Maybe you can do something about it. So if we have the data, we have AI, let's try to go one step further. So that's it. Please reach out if you have anything, constructive feedback, destructive feedback, all sorts, and happy to take questions.
Destructive. You open to take questions?
Yeah. Do you have time?
Good job, good job.
Thank you.
All right, any questions, guys? We have 5 minutes. Go ahead. Get the mic.
So you perform the forecasting completely based on the images. Did you consider other factors, whether the patient is getting treatment or not?
This was solely based on the images, but just because it was kind of the first approach. But you're totally right. If you start adding electronic health records, there is I don't remember also who said that. I'm good at quotes, but not to remember who said them. That they say that the thickness of your file is a good predictor of how long you have before you die in case of the hospital, because it's one of those biases, right? You start introducing the model. Let's introduce all the data about the patient. And sometimes the predictor is how many times you came to the hospital. That's a good predictor that you probably have something wrong with you. So I haven't tried, but yes, it should definitely be considered. Thank you.
So my question is this model, first of all, in production? Second, are you helping more radiologists or brain surgeons? And do they trust?
Yeah. So let me actually, this brings back to the first problem we had, the COVID one. We worked on it for about 6 months and we got a model. When we tried to productize that and tried to help people who were coming to the hospital, we figured out we could not put in production because we needed in real time, the images, the chest x-rays, we needed the electronic health records, all of this in real time, and a way to send back to the doctor. None of these exists. The chest x-rays and radiology electronic health records is another part of the hospital, and there is no communication between them. So we showed the university there is this blind spot that they're now trying to fix. And out of the 20 institutions, I've heard, I think only Harvard was able to somewhat put that in production. None of the other 19 were. For oncology, I think we are helping primarily the radiologists who have so much workload. You're like, I do not want to be looking at 30 patients an hour because I'm going to end up making a mistake. So help me out. When he brought the volumetrics to the neurosurgeons, they were so happy because now they can see exactly where they should be removing. And they're like, oh, this is so helpful, thank you. So in the end, it ended up helping the neurosurgeon too. It is in production as in with the human in the loop. We have right now at UCSF, they're using it, but always goes to a technician who looks at segmentation, looks at makes choices about changes the segmentation if needed to. Then it goes to the radiologist who makes a decision, who then sends to the neurosurgeon. So,
yeah. That's amazing. Thank you. Thank you very much. Any other questions? Go ahead.
Thank you for the great presentation. And my question is regarding dataset bias. It's very common for us to do data augmentation in self-driving car industry to reduce data bias to create model generalized to another domain, right? Yeah. So for the medical industry, I wonder, for example, we have patient data collected with tumor usually happen at one side of the brain, but because of this dataset bias doesn't mean that other patient, the data we need for medical industry. The question I have is, do we also do this kind of data augmentation, like view transformation, data manipulation to create more unbiased data for medical images?
Yeah, thank you for the question. It's super important, and there are a lot of interesting things going on in this field, in particular in the area of self-supervised learning and adversarial attacks or adversarial networks. The idea there being there are some papers that have shown that the model might give a segmentation that does not work so well for African Americans, for instance. And what they do is that they add a branch of adversarial network just to try to predict, can you look at this brain and tell me, for instance, the age of this patient? Can you look at this image and tell me whether they are Caucasian or African American or this and that? By doing so, this network starts to learn a representation of what's the difference between a Caucasian and African American. What's the difference between a 50-year-old and a 14-year-old in terms of the brain? And then these representations actually turns out to help a lot with biases. So as long as you have an idea on what the bias might be, then you can try to introduce that in the network. But unfortunately, the way that usually we learn is after the fact. We run something, it didn't work, and we're like, why didn't it work? Oh, because the poor quality of the scanner. Okay, let's try to add that as a branch in the network. Learn that there are good and bad scanners. Not every scanner is like UCSF multi-million-dollar scanner. Go try to put that in the network, and that's where I think the human in the loop is important. Make sure that those mistakes don't go into production.
Yeah, great presentation. Thank you.
Thank you.